Thank you very much. This presentation is really a report from involving many authors, and you see them here. Several of them are actually in the room, and really summarizing what was discussed during a workshop that was called Improving Climate Models and Projections Using Observations. And it's very relevant to what we talk about here, what we already said earlier. And for instance, Hans made that point, model biases are the enemy of any reanalysis, I would say, and model biases are the enemy of any climate modeling. And so we really thought about during this workshop what can be done. And I will just quickly go through a couple of slides, just that you know I will slow down later on, to set the stage. And the problem is we actually have a lot of benefit from the models. In fact, all the IPCC work and so forth is based on our climate models. And the decision or the conclusion, humans impact climate, all come, or to a large extent, come out of our climate models. We nevertheless know that these models are prone to biases, and we worked on these biases for decades now. And it's not just in NWCP models, we have biases everywhere with big temperature differences, of course. And so curing these is actually a problem, and it's in all parameters that we see, including teleconnections and dynamics. And it also shows up really now more and more on regional scale. And there is hope that with increased model resolution, you might be able to do something. In fact, I showed this. This is in fact a coupled run that is from, let me actually see here, it's GEOS Echo Sea Surface Speed. It's really a coupled model, 1 kilometer. I'm not sure how long this was run, but whenever I steer at a figure like this, it's actually incredible what kind of details is in this. And of course, these are the first examples, and you can actually do a lot doing these runs over a long period and reducing model bias. I think we are far off. And so even if we would get there, is always a very great chance that there will be some biases in some form that we need to cure. So the other thing is that the more we go now into regional climate change and variations, we also see that in particular on the regional scale, there's even more biases showing up. And for instance, this is the heat wave last year, 2023, in the Atlantic. Models were not really capable of simulating this. And it's very clear that we, first of all, we have to explain it, we have to understand it, but we also need an effort, really an effort. That means there needs to be a group coming up and money being there to start resolving this. And of course, any problem you can also define as an opportunity. And I think there is a great opportunity to start approaching these problems. And one of the things, the consequences, of course, we have to be clear, and that holds for reanalysis, for weather forecasts, and so forth. Whenever we have these discrepancies, it is very hard to explain the results to politicians or to decision makers, and it's much better really solving this. And we can do this in a model hierarchy approach, really using various different models to understand these problems and see which models are better, which are worse, or which resolution is better. But the point I tried to make already earlier today is that data assimilation really needs to be an integral part of this approach. It's not sort of something offline, and we really have to move this forward. And there are different uses of data assimilation in this context, and it's also the use of expensive climate observations in the modeling, in the improving the model. And the immediate things that come into mind, where does data assimilation come in, is in the context I just talked about, is actually inferring uncertain model parameters. It's a parameter estimation. And I've talked on before and afterwards is also then, of course, improving the initial conditions, for instance, for seasonal forecast, for decadal forecast, and so forth. And quantifying uncertainties, we have seen this already with Kalman filter, that you get uncertainties out, and of course with different approaches, not quite as easy, but this is the idea that you really bring this into, in particular, estimate model parameters that help reduce the biases. Should be clear that we have approaches, we have parts of it, but if we really want to realize this in a full scale, we need a lot of development. Continuous development before we can come to something what might be called a system reanalysis, because it's the assimilation, it's the technology development, it's even the creation of the next generation. Looking around, some of us, including myself, are getting out soon, and we need to get the next generation in also on the technology development. And of course, if it comes to a full Earth system reanalysis, we need to get the carbon in, we need to get the ecosystem in, and soil moisture, and many things that are not yet properly resolved. And then as I said, we have a couple of elements in place. Sometimes it's competing. It's almost like religions differences, but at the end we have to learn how to bring this together in hybrid ways, that we really take one and the other in ways that at the end we can form a system that takes the advantage of whatever it is, including machine learning. And I think it also should be clear, machine learning is not the cure to everything. We already see quite some problems with machine learning, and so we have to take whatever advantage is and bring it together. That's development. Laura talked about sparse data. That's our problem. We cannot actually redo all the observations that were not taken over the last 100 years. We have to live with what we have, and we have to use it to actually come up with climate-type reanalyses. There are more processes. I mentioned already carbon. There are other things we have to include, and then of course if it gets to higher and higher resolution, we have to deal with chaos, with nonlinearities, with phase transition, and so this all really requires development. And as I said, I'm reporting about a workshop that discussed it, and what follows is really what came out of this workshop. There was a publication, but I think it's worth mentioning this here also because some program managers here, and I think there's money required to approach this. But essentially, if you want to do the next generation reanalysis, or in fact the next generation climate modeling, really bringing climate modeling, the observations and the assimilation together, there are all these points which have many aspects underneath that needs to be addressed to really solve the assimilation problem. It starts with the improving the use of observations. We have many observations, but we have to use them much better. Develop the AD tools, automatic differentiation tool, and machine learning infrastructures, and to move this to the next generation computers. I mean, the hardware is actually moving underneath us, and we have to sort of follow it. Advanced ensemble and variational data estimation methodologies, machine learning theories, deal with sparse data and so forth. Model improvements through parameter estimation, and we can do it, we start to do it, but we have to learn how to do it better. And then, in fact, perform Earth system reanalysis. It was never really done in a full scale like we have atmospheric reanalysis. If we want to do a full Earth system reanalysis, including the carbon, that is a learning process. And we know 30 years are quickly over. And then at the end, we want to use it like the 100-year reanalysis to learn, to really get more insight. And for the remaining a few minutes, I just want to get quickly through this. You all have the slides, and you can do this further. So I don't have time to go through all this, but the first point is we really have to learn how to better use the information in the existing observations. And the first point is we have something like Ops4MIPS that was created to, in fact, confront climate models with observations, but assimilation needs more. In fact, the observations in a different way, ideally as raw as possible. And I think at the workshop we said we need something like Ops4ASSI. So for the assimilation, we really need to develop this. We need to generate reference data sets that are bias corrected, that are as best as possible, that everybody can use it, that we have some standards. Study information content that includes correlation, error, covariances, and so forth, but then data archaeology. This is actually something, there are many observations from the past still somewhere on paper, and I don't really see any funding to move these into the same system that we have all the other data. And I think that can help a lot. And Laura already alluded to this. And then identify gaps. Of course, the assimilation can help really improving the data set. And this is just one example. It's actually altimetry development from CSAT in 78, I think, to what we now have with the SWOT data set. And you can see there's really a huge improvement, but also we have to learn how to use this improvement in the assimilation content over longer time series. The 80 tools, the machine learning, automatic differentiation, we have compilers. Unfortunately, the people who know how to do this come to the retirement age, and we really have to make sure that we preserve the know-how that we have and move this forward, but also move it to the next technology of hardware, deal with the next generation of hardware and so forth, develop toolboxes to this, also cookbooks how to do this best. This is all stuff that needs to be done. It might not be so sexy, but I think if we want to move this forward, we have to do this. We know how some things can work. Most of what we use is actually linear theory, really moving forward into nonlinear, chaotic applications. We have some ideas how to deal with it, but how to best do this, we have to learn. And that's actually where the theoreticians, the applied mathematicians have to come in and help us on this, deal with sparseness and many other things. And then develop really the hybrid tools that we need to do this by using really the individual parts and put it together in something new. Parameter estimation, we have first examples, and I think there can be done a lot with it, also in terms of bias corrections. Assimilation is not just to create an initial condition. I think the biggest impact I see for climate assimilation is to parameter estimate, to bias correct, and then do a forecast or projections of these models with a much improved climate. And then actually do the Earth system reanalysis. That's also something we're learning by doing, but we have to really identify the parameters, the uncertain parameters, include new parameters, including carbon, soil moisture, maybe even waves, other processes that are not yet in there. At the end, the communities, the decision makers wants to know at some point, where are the carbon sinks, where are the carbon sources, or the CFC sinks, or the CFC sources. These systems will be able to tell us by backtracing, by doing a lot of things, and that's where the decision makers or the monitoring of the hopefully mitigated system needs something like this in the future. I just want to make a plug actually for a poster that Armin Kerr will present tomorrow, because it's the first example of a pilot Earth system reanalysis that we did or are doing in Hamburg using a model. It's called CSAM. It's actually a coupled intermediate complexity model from which we get the A-joint used in a compiler. We have the A-joint to this model, and Armin will present this very briefly. This is an example of how you can remove biases through this. It's actually almost 40-year-long Earth system reanalysis. It's a pilot, so we would never actually sell this as the best state. But you see, for instance, the biases of the first guess or the first iteration in cloud cover. I hope you can see it. And after 40 iteration, we can mostly remove this. Surface solar radiation, surface thermal radiation, and top of the atmosphere. So the left column is always we start with this, and through the parameter estimation, you really can come down with this. The radiation part is actually the easy one. We have to learn how to deal with the dynamic aspect. The resolution is important. Armin can tell you this full story, so go to Armin's.
Detlef, can you wrap it up?
Yes, I do. So we also improve, for instance, precipitation. This is GCP, and after the iteration, you see on the left side the AMOG. So I said understanding is really what we want to do, but maybe I just leave this here. I think this new framework, we have to develop this for Earth system modeling, calibration, analysis, estimation, assimilation, and I think we can do a lot with this, and that's my plug, that we really think beyond reanalysis, just reanalysis, to really think in this framework, and it would be great if we can initiate this here. Thank you.